We're in the chapter on general relativity and astrophysics, and this is section chapter 38, and this is 38.3. We're going to be looking at the rotating platform. We just finished looking at the elevator experiment, and we concluded in the elevator experiment that a theory of acceleration, which is what we are seeking here, is also a theory of gravity, and conversely, because gravity and acceleration cannot be distinguished. Einstein there, you recall, proposed that gravity itself would bend light. Therefore, acceleration will bend light. And that was proven to be correct. Now here we're going to look at a rotating platform. And this rotating platform will be very simple. Imagine a large disk with an angular velocity omega, and therefore spinning about a given point. And so a particular point here will have a velocity v, which is r times omega, you recall from our study of angular momentum. Now, as we move further and further out, if this disk is large enough and omega is large enough, this velocity will approach the speed of light. Until then, the circumference, of course, is 2 pi r. But further out, the circumference is going to be equal to this circumference, c naught, 2 pi r, times the Lorentz contraction factor, which is 1 minus v squared over c squared. Now, as this v becomes very, very large, so I get way out here, of course you'd think there's a huge distance around the circumference, but at some point the velocity begins to get close to the speed of light. We get 1 over 1, 1 minus 1 is 0, and so the circumference around becomes actually 0 or near 0 if we get far enough out. If we were to plot this circumference versus the radius, of course it goes up linearly. It's increasing as circumference is proportional to the radius, but then at some point it begins to fall off, and then it dips very rapidly down to 0 when our velocity is approximately equal to the speed of light, c. Well, that is a very strange thing, that the distance around a circle gets larger, 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 then it begins to get smaller and smaller and smaller, until finally the distance around the circle way out there at large r is 0. Well, that's not the only thing that happens. This happens because of Lorentz contraction. But let's think now about what happens because of the time dilation. If we have a set of clocks at different distances from the center, then of course they will all agree that a time t naught passes between two events. But once we get out here with high velocities, then our time is altered, so the time becomes equal to the normal time divided by the square root of 1 minus v squared over c squared, which is the Lorentz, which is the time dilation. And so our lengths get shorter and shorter. At some point, our times stretch out further and further, and therefore it follows that clocks way out here, near this limit where the velocity is equal to the speed of light, those clocks almost have time standing still. If you were to walk out here, time would not evolve. You could wait out there you're almost going the speed of light, and you're feeling enormous acceleration, remember, because you're going around. But however, because of that, your time is going to almost stand still. Why is that? Well, what would normally take, say, 1 second right here, as we go out and velocity is very large, this becomes c over c, which is 1. 1 minus 1 is 0. Square root of 0 is 0. Dividing by 0 gives us almost infinity. So this time for 1 second becomes an observed time of almost an infinite amount of time, between 2 heartbeats, say. Therefore, things that happen out here appear to be incredibly slow. People could go out there and live what they thought would be for 5 or 10 minutes. If they came back, their relatives near the center of the circle would have aged by several generations. Their friends and so forth already dead, and their children even dead. Well, in both of these equations, the velocity is r omega, where the angular velocity, omega, is the angular velocity of the platform. Well, we can see here that in accelerated frames, time slows down and distances contract, and your geometry of space and time is not Euclidean. It's not flat. It isn't like we have where normally parallel lines never meet. Here the parallel lines can meet. Time runs at different rates at different places in this space, and therefore we can say that our four-dimensional space-time, x naught, x, y, and z, and this x naught you recall is ct, that this four-dimensional space behaves in a curved manner. It's curved because at different places the distance that we would normally expect can go down to 0, and we find that back in our elevator experiment that we showed the same thing, that this curved space and time was similar to a gravitational field, if that gave us our acceleration. So what we can conclude is acceleration is the same as gravity, and that gravitation near a mass, since a mass gives us gravitational acceleration, that mass will give us a curved space-time. So this gives us something very bizarre. How do we now begin to think about a space and a time where time runs at different rates to different people? The distance around a circle is no longer 2 pi r, and things of this nature. Almost everything that we used to think about. And in fact, even the light from a star coming near a mass will be bent. So in fact, light can go on 2 paths around a star with a lensing effect. And we have now observed this astronomically, which is truly remarkable. And when we look at this star, we'll actually see 2 of them in different places. How do we begin to talk about such a mathematical theory? We'll take that up in the next section.